What is crack-lackin', my G's? Today we'll be learning about ionic, covalent, and metallic bonding. So let's get right into it. So we'll see on my screen now that we have a periodic table, and the first one we're going to learn about is ionic bonding. So ionic bonding is between a metal and a non-metal. So metal is basically all the red here, and non-metals is the blue, including hydrogen up in its teeny corner over there. So, for example, if we have Na2S, so that's basically sodium sulfide. How does this work? How do they bond? Well, first, you got to realize that sodium is a metal and sulfur is a non-metal, right? It's right there. So, sodium has 11 electrons and it's in row 1. So that means it only has 1 valence electron, while sulfur has 6 valence electrons since it's in the group 6. So what is so important about valence electrons? Well, they dictate the bonding properties of an atom and their chemical properties as well. So how are they going to bond? And basically stuff like that. How are they going to bond, basically? What are their properties after they bond? So sodium only has 1 valence electron. So if we were to write out sodium as a Lewis dot structure, we have Na and another Na because there's 2 of them. And then we have sulfur, which is 6 valence electrons. So we're going to have 1, 2, 3, 4, 5, 6. So we have to satisfy the octet rule. So the octet rule states that for a stable outer shell, an atom needs 8 valence electrons. So what's going to happen is that because sulfur has greater ionization energy, which means that it's more likely to attract electrons than sodium, sodium's going to give away its valence electron because it makes sense. If sodium has only 1 valence electron, if they were to give it away, then they would fall to their previous full outer shell, which would make it stable. Sulfur, on the other hand, is not likely to give away its 6 valence electrons because it's only 2 away from having a complete outer shell. So that's why it's more likely to gain electrons. So sodium will become something called a cation. Sulfur will become an anion, which means that it's negative, cation, positive. And so if you were to write it out, we'll have Na plus, technically Na2 plus since we're giving away 2 of them, but and then sulfur, which is 2 minus. So that's basically ionic. And one more thing I forgot to mention, and it might be obvious, but opposites attract. Cation is positive, right? These are positive. Anions are negative, and a positive and negative attract. So that's why that electrostatic attraction right there, that's what's going to bond these 2 elements together. And the resultant will have its own unique chemical properties. So next, let's go on to covalent bonding. So covalent bonding is between a non-metal and a non-metal. Oh, shoot that. Non-metal. So basically, it's between the blues right here on the periodic table. So for example, if we were to have hydrogen and oxygen. So what we'll find is that hydrogen, again, it goes back to the valence electrons. Hydrogen only has 1 valence electron, while oxygen has 6. So 1, 2, 3, 4, 5, and 6. And I forgot to mention, just like last time, we're going to have another hydrogen. And you might find this familiar. This is H2O. H2O is covalently bonded. And when you bond with other molecules, this will be a hydrogen bonding, but we can get to that later. For now, this is just a simple covalent bond. So what's going to happen is that unlike in ionic bonds, where sodium gave up its electron to sulfur, in covalent bonding, what's going to happen is that oxygen and hydrogen are going to share their electrons. They're going to share the unfilled electrons to basically, you can think of it as like temporarily having a full outer shell. While in ionic bonding, you have a complete full outer shell for both atoms. In hydrogen and oxygen, or basically covalent bond in general, they're going to have a temporarily or like sharing of electrons to temporarily have a full outer shell. So what's going to happen is that these in hydrogen and oxygen, the atoms are going to be shared. So what we're going to denote that as is with a line. This electron pair line. Electron pairs for 2. So this here can show that there's 2 electrons being shared, one from hydrogen, one from oxygen. Now, under covalent bonding, there's something called non-polar covalent bonds and polar covalent bonds. Now, how do you figure that out? Basically, to figure that out, what you need is to find the electronegativity differences in the bond, in the covalent bond. So what you'll see added is a little periodic table that instead of showing metals, metalloids, and non-metals, we have how electronegative the atom is. So as we'll see, as we start from the bottom left and we go up, the electronegativity increases. And as we go right, the electronegativity again increases. Now, this is because as you go up the periodic table, it's a bit complicated, but as you go up the periodic table, there are less electrons. So that means those electrons will be closer to the protons, and there will be a very strong attraction between those two. That's why there will be a strong electronegativity force. But as you go down with more electrons, there's a shielding effect where the electrons before them will kind of block off the electron power in front of them. It's a bit complicated. I can't word it right now correctly, but that's not the point of this video. We're learning about covalent bonds. So basically, if you want to learn if for example, water is a polar covalent bond or a non-polar covalent bond, we'll have to look at the electronegativity differences. So oxygen, as we see, is 3.44. So 3.44. Now we subtract that from hydrogens, which is 2.20. 2.20. So when we subtract that, we bring down the 4. 4 minus 2 is 2. 3 minus 2 is 1. So 1.24. And to figure out if that is polar or non-polar, we'll have to see a little comparison. Okay, so I'm going to erase a little bit of this. Basically, it's polar if the electronegativity difference, En, is greater or equal to 0.5, which is the general number, and if it's non-polar, if it's less than 0.5. So in this case, 1.24 is greater than 0.5. So that means that this is going to be a polar covalent bond. On the other hand, if I had something like methane, which is the chemical formula for it is CH4, we can figure out how to draw its Lewis dot. So carbon. Now carbon's a pretty amazing element because without it, we would not exist. What's amazing about it is that it can form 4 bonds, which is a pretty high number. Because you see, as we go right of carbon, the amount of bonds made decreases, and so does it as we go to the left. So nitrogen only needs 3 bonds, oxygen only needs 2 bonds, and fluorine only needs 1 bond. Same with boron. Boron only needs 3 bonds because remember, it's more likely to give away its electrons because remember it only has 3 valence electrons, so it's more likely to give them away. That's why it's going to form 3 bonds. But I got ahead of myself. Let's look at hydrogen. So hydrogen 1, hydrogen 2, hydrogen 3, hydrogen 4. So this can form a bond, this can form a bond, this can form a bond, and if I wiggle my way in there somehow, that can form a bond. So I'll clear this up a little bit so it's not so clustered. Basically, if we draw it out, we have carbon in the middle, we have hydrogen here, hydrogen here, hydrogen here and another hydrogen here. Now, is this nonpolar or polar? Well, let's look at the electronegativity differences. So carbon has an electronegativity of 2.55, whereas hydrogen only has 2.20. So 2.20, we subtract that, there's a 5 minus 2 is 3, 2 minus 2 is 0, so we get 0.35. Now, according to the rule we made last time, 0.35 is less than 0.5. Therefore, this is non-polar covalent. And the final bond we'll look over is metallic bonding. So this is between a metal and a metal. Now, this one might be the weirdest and maybe might be the most kind of difficult to understand, but they are very important because if you look at the periodic table, pretty much more than like 80% of the entire thing is just metals. So it's interesting to explore how does the majority of the elements in the periodic table bond with each other. So I can't really give examples for this, but in metallic bonding, what's really going on is that you have some atom, let's say in this case vanadium, okay, and vanadium has whatever amount of valence electrons. What happens is that these valence electrons, or just the electrons in general, become delocalized, meaning they basically kind of just drift off from the central atom, but there's still an electrostatic attraction between them, because since they basically became delocalized, remember, when delocalization basically means that they just kind of went away. There's no central point where they're around anymore. This makes vanadium become an cation. Remember, cations are positive, and electrons are negative. They're negative, remember. So what's going to happen is that there's going to be an electrostatic connection between the central cation and the delocalized electrons. And that's basically going to be your metallic bonding. So what's going to happen next is that other metals, like for example chromium, that's a bit small, like chromium, they're also going to have delocalized electrons. So what's going to happen is that there's going to be a big sea of electrons between the cations, the central atom, and the delocalized electrons, and that's what's going to hold these elements together. So really, if you need to take away anything from this, it's that opposites attract. That's really what's going on here. We just put up naming conventions of ionic, polar covalent, non-polar covalent, metallic, but we're just exploring how do these atoms have opposites and they attract with each other. So let's move on to some practice problems. So what we'll see on my screen here is that I have six different chemical compounds, and your job is to identify them. So you can go ahead and write these down in the comment. The answers will be in the description. And I guess that's it for today. Thank you for watching. We'll see you next time. Bye.